All right, it's my pleasure to introduce our speaker at today's colloquium, Tony Tyson, distinguished professor of physics at the University of California at Davis. I remember almost half a century ago, right after his PhD, Tony burst into astrophysics with the null effect of gravitational waves. And this made a big news. You wonder why a null experiment would be important. But it was important because at that time, Joe Weber, an innovative instrumentalist physicist, for the first time decided to build a detector for detecting gravitational waves. And he had built some big cylinder of aluminum, of the size of this width of this room, and way high. And he was observing for a few years, and he claimed that he was seeing a lot of gravitational wave. In particular, it was coming from center of a galaxy. The equivalent energy was that 100 times that we expected to be. Clearly, this was big news, and so a lot of people tried to replicate this experiment, and Tony was one of them. But we had, I think, Peter Michelson and Fairbanks also tried one here too. Mm-hmm. But Tony was first to show that those gravitational waves didn't exist. Well, this was not also important because it paved the way for other methods to detect gravitational waves, in particular the LIGO experiment, which most of you have heard about, has been very successful in detecting it. Well, Tony, right after his PhD, worked for 35 years at Bell Lab, and he did many innovative experiments. Among them, something relevant to the talk today is that he applied CCD, newly discovered CCD detectors, to make deep observation of astronomical sources, in particular finding galaxies about 3 to 10 times dimmer than most people had observed at that time. And this observation led into the idea of using this observation of galaxies to do weak gravitational lensing, and eventually led to the topic of his colloquium today. Well, he has led this effort, international effort, to build a new kind of telescope. It's a called Large Snopstic Survey Telescope, Observatory telescope, or LSST, which recently was changed the name to Vera Rubin Observatory, one of the leaders of discovery of dark matter. And he has served as a director from 2003 to 2013, and he continues to be the chief scientist for the project. Tony received his PhD actually at Stanford, the physics department, in 1962, and PhD from University of Wisconsin, 1967, majored in condensed matter physics. He has had many awards. He's a fellow of the American Physical Society, American Academy of Arts and Sciences, and he's a member of National Academy of Sciences and American Physical Society. So it's my pleasure to invite Tony to tell us about the past history of LSST Rubin and its potential for future observation.
Thanks. So, thanks for the kind words. This has been a fun experience for me, and it's an experiment that I started in '96. So,
bit louder.
Yeah, it's an experiment that I started in 1996. And I'm just going to go through a little bit of the early history. And then I'm going to transition about halfway through the talk to a problem that has crept up recently, which is the interference with optical astronomy from low Earth orbiting communication satellites. And I've been spending a lot of time worrying about that and working with the industry folks. So let me turn this puppy on. And so we all know that the universe is mostly made of stuff that we don't know anything about, which I find exciting. It means there's new physics out there, dark energy and dark matter. This is a nearly edge-on picture of a galaxy, M31. And why am I showing you this? Because Vera Rubin and Kent Ford got together at the DTM in Washington and decided to apply a new imaging spectrograph that was faster than photographic plates to look at different parts of an edge-on galaxy, and lots of them eventually. And she confirmed something that was already discovered earlier, but had been neglected, mainly Fritz Zwicky, in the 30s, actually starting in the 20s and then all the way through the 30s, had found that galaxies moving around in clusters of galaxies were going much faster than the local speed limit, which was set at, if you assumed 1 solar mass per solar luminosity, and apply that to these clusters of galaxies, the galaxies would fly apart, and the clusters existed for a long time. So he called it missing mass, and in German he called it dark matter. It was forgotten because the war came and people forgot about this. And so Vera started looking at these galaxies and measuring the velocity on one side versus the velocity on the other. This is just showing you one side where the velocity is measured. And the way she did this was with emission lines from gas and stars and gas. And her measurements are shown here in yellow. And it disagreed with what one would expect if you assigned 1 solar mass per solar luminosity, which is the Keplerian light curve shown in dashed below. And so it was realized by many that this was a confirmation of what people had known earlier from Zwicky's observations. And then Mort Roberts at Caltech said, okay, well, why don't we look at the 21 centimeter line of hydrogen? And he continued this observations up here. So if you just do simple math, a half mv squared equals potential energy, you can see that what you require is these galaxies to be embedded in something that has a huge core and is not distributed like the light at all. And so this is fun. So I'm going to be talking to you about cosmic evolution and how that plays into this experiment. So here's the Big Bang, cosmic microwave background, and then the galaxies formed. First stars formed and were very hot, and then dark matter existed during this period of time, tending to slow down the expansion. And then only recently was it discovered that the universe accelerated its expansion. And there's a couple of instruments that I'm going to talk about. This is the LSST. And this is a satellite for CMB. And so the issue here is, how are we going to find the rest of the mass in the universe with some experiments? So if you're on the Earth at a telescope and you're looking out at the distant universe through a big overdensity of dark matter, and you look straight through it, and just by chance there's a round galaxy somewhere around there. And what happens is, of course, if Einstein taught us that the light from the galaxy travels a different path, because it's going to be bending by 4gm over RC squared by an angle here, and you see the galaxy in a different place. Actually, every pixel in this galaxy is mapped to a new place in the sky by that angle. And now imagine that you have billions of these galaxies, and this is basically a cosmic mirage. And with all mirages, if you understand the physics behind the mirage, you can invert what you see to get a picture of what caused it. This works for ships over the horizon, and it also works for these experiments. And so we started doing these, I started doing these experiments in the 70s, and started seeing lots of cosmic mirages in the sky, and I'm going to describe that journey. But here's an example of a combination of weak and strong gravitational lensing. Here's a galaxy out here, and here's a cluster of galaxies, but you don't see the mass, but there's a lot of dark matter holding the cluster together. And the light from this distant galaxy can travel straight through. So if you're here on Earth, you can see the galaxy in the center, faintly. And then light can also travel a different path, as I showed you, and it appears at a different place in the sky. And if you have everything arranged right, you can have a so-called Einstein ring appear in the sky. And this has been seen in numerous images in recent years. So we went out and took a lot of data, both HST data and ground-based data. This was in the mid-80s, just as HST was coming online. This is a picture that we got of a cluster of galaxies at a redshift of 0.4. The galaxies in the cluster are these yellow things that you see. And you can see parts of the Einstein ring around here. You can see multiple images of that galaxy that's at the center out here on the Einstein ring, and here's the galaxy at the center. And we combined the strong gravitational lensing with the weak gravitational lensing in this picture, and you can't see terribly many of these little arclets, but they exist all around in the data. There are a few thousand of them that we used. And we had so Bell Labs gave me a lot of time on a computer that they wanted to get rid of. It was, at that time, one of the best crays around. And I had a whole year on this cray and did a giant Monte Carlo experiment. And this is the result. I had a lot of point masses that were floating around, and also some diffuse mass. And this is what we found. It's sort of interesting, actually, because these spikes are the individual galaxies that, after the fact, identified with the galaxies that are in the cluster, and they're at the same position. And then there's this giant sort of Gaussian overdensity of dark matter in the center, and that was something new. And that's been seen in recent data as well for other clusters. These galaxies in the background, of course, were very far away at a redshift of 1 and 2 and 3. And they were very blue because they were forming their first stars. The first stars burn very hot, and they have a lot of flux on the ultraviolet, and the ultraviolet is being redshifted into the blue. So they're blue instead of red, as you might have thought. So back then, at the beginning, the universe was quite diffuse. This is a computer simulation of dark matter as a function of time during the evolution and expansion of the universe. As it went on, it became overdense. Overdensities of dark matter created more dark matter piling up and created voids in between, and so it became very more filamentary. And then here today, the universe is quite filamentary. So that's what it should look like if you're able to map it. There's something other than the so-called gravitational lensing, galaxy-galaxy lensing that I showed you in that previous plot. There's something else that you can do. You can look at all possible pairs of galaxies in your data at all possible redshifts, and you can correlate their shapes with one another. This is something called cosmic shear, and this depends on a different way on the unknown parameters in this model than the galaxy-galaxy lensing. And you want to, so a typical signal for cosmic shear, so what's happening is that light from a couple of galaxies that are sort of close by in the distant universe follow similar tracks through the intervening dark matter, and they get deflected in similar ways, so their ellipticities are quite similar on the average. And then something is different, of course, somewhere else in the sky, and those ellipticities are similar, but there's a difference between these two. And in the cosmic shear signal is encoded the actual power spectrum of dark matter as a function of look-back time in the universe. A typical signal is only 2 by 10 to the 3, 2 by 10 to the minus 3. So in terms of shear, in terms of the shape, ellipticity, and you want to always get a factor of 10 better than the signal in order to get a good signal-to-noise ratio. So the thing to shoot for in terms of systematic error is 2 by 10 to the minus 4. And to do that, you really have to try hard. And it would be impossible to do unless you were able to combine experiments. And so by combining the galaxy-galaxy lensing that I showed you before with the cosmic shear, you have one example of a multi-probe precision measurement of cosmology, and it just gets better, as I'll show you in a few slides, by combining it with yet other experiments. Okay, so if you were to put graph paper behind, in a simulator, behind that gravitational lens that I showed you, that cluster of galaxies, it looks like this. Greg Kuchansky and I at Bell Labs did this experiment on a computer, and it actually looks like this. And you can see very faintly in red the individual galaxies in the cluster, and that's what it would look like. And so our homework assignment is to directly map the warp of space-time back to half the age of the universe. And that's what this facility, which we now have named after our friend Vera Rubin, is going to do. It's almost finished, and I'll show you soon. Well, to do that, you have to gather up all the very best scientists and engineers you can, and that was how we started the project. This is about half of the number that were working on the project at the time this was taken. I think this was at SLAC. It looks like it was at SLAC, this picture. You get a lot of really clever people together and design the experiment. And so I'm going to talk first about the experiment. This is old slides from those years, because I'm talking about the history, but it hasn't changed. This is the Rubin Observatory slide that we have today, showing the telescope, which we named after Charles Simoni, who allowed us to make the mirror for it, and so we named it after his family. And the camera, and obviously not to scale, the camera is supported up here in the telescope. So the telescope has a mirror in it, collects a lot of light, nearly 8.5 meters across, We have a camera here, which I'll show you a little bit better picture in a second. 3,200 megapixels. Each image that we take with this has a size of about 44 full moons. It's about 10 square degrees or so of the sky. So it's a wide field facility, and it scans the sky a couple thousand times per night. Takes all these images that last maybe 30 seconds, a couple of thousand times a night, and we continue this for 10 years, creating a digital color motion picture of the universe, which is valuable for a lot of science. So it's a 10-year survey, and we're about to begin it very soon. I'll show you some the current state of the project. It'll come up with about 37 billion stars and galaxies, and 10 million alerts per night, broadcast to the entire world. So if you guys give us your cell phone numbers, we'll ring you every time. 37 billion stars and galaxies, 10 million alerts a night, and 20 terabytes of data every night. Eventually adding up to about 200 petabytes of simulated and real data to analyze. And so this is a chart that I made early on in the project showing the something called the étendue, which is important. It's an optical term that's used by optical folks that give you an idea of how much light you can collect per unit time in some kind of optical facility. It's the product of the number of square meters in the aperture of the camera or the telescope, whatever you got, times the number of square degrees in that field of view, field of regard. And so it's the product of those two things. This is particularly useful for galaxy experiments. And on the x-axis, so that's on a log plot. I should point out this is a log plot. And on the x-axis are various different facilities, going from the Sloan Digital Sky Survey up to Dark Energy Survey, Subaru, Hypersuprime Cam, Pan-STARRS, and LSST. And you can see that if you just go into the survey mode, which is the percentage of time these facilities do surveys, you get a factor of about 50 larger étendue with our facility, which means that you can graduate from having millions, maybe 100 million objects to having tens of billions of objects. And so now, instead of having statistical sample noise, you're limited by, guess what? Systematics. That's the only remaining issue. Okay. So the mirror was a contentious thing initially. We thought initially we were going to have 3 separate mirrors. But the way it finally shook out is that we end up with making a one mirror that's shown in the bottom here, and carving out, grinding and polishing it, 2 mirrors in it, a 8.5 meter wide annulus primary, and then an inner f1.2 very fast mirror. And so the light goes down from the universe up into the secondary, off the primary, into 3 optical elements in the camera. So you have all sorts of, and all of these in principle are, and in fact are aspherical optics. And so if you do your optics right, you can actually get very pristine images over a very wide field of view. And so that's how, and the camera isn't shown here, it sits up here. So it's always been true that the technology drives astronomy every epoch, starting in the early days, and it continues today. So in our project, microelectronics, we went beyond the current state of the art in microelectronics, and that comes in twice. It comes in through the silicon fab. It comes in to the number of pixels that you can have in your camera. That's silicon fab. And it also, by the same token, comes in the data analysis because it comes in the number of transistors that you can have in a CPU. And so simultaneously, it's a double gain. You can handle the data off of a bigger focal plane, which is nice. It comes in twice. But we pushed it beyond current limits at that time. Software, we pushed beyond limits. We're still pushing. And large optics fabrication, which is something I just showed you. That had not been done before. And so here's the promised cutaway image of the camera. You can see the focal plane here. We can get, at any one time, we can get 5 of these circular color filters in this can that contains the CCD and the electronics and everything. And so there's a device that moves these filters into place. And this is just a conceptual drawing of the focal plane layout. We have 21 so-called rafts. These are 9 CCD arrays of 3x3 arrays of CCDs and so there are 21 rafts in the focal plane, and here's the moon for scale. And so it's the CCD. So the facility is going to do a very wide, fast, and simultaneously deep coverage of the sky, and this has not been done before. People have done wide, they've done deep, and they've done fast, but not all 3 at the same time. And this allows us to do all 3 at the same time, and that's where we get our science. 37 billion objects in space and time. Each patch will be visited over 800 times, about 1,000 times during the survey. 30 trillion measurements, 30 trillion photometric measurements. And we are sensitive to things that move and flash in the sky. So here's a previous survey that we did years ago called the Deep Lens Survey. On the left is one picture taken at one time, and then a little while later, another picture on the right, in the middle. And on the right, you see the difference. So something flashed between those between those times, and we're going to discover thousands of these, millions of these every night with LSST. And so we can search for areas in astronomy space that have been so far unexplored by doing that. And here's an example from Rao et al. Earlier on, showing a plot, log-log plot of y-axis magnitudes of the explosion. So this is really bright. So minus 26, these are GRBs, gravitational bursters, gamma ray bursters rather. And then on the x-axis is the decay time of the explosion. And they're all, on the right-hand side, there are all these things that are known to astronomy that we know and love, of novae, supernovae, etc. But in this, there's this whole unexplored region on the left that that LSST will be able to probe, starting as soon as we get on the sky, which is a lot of fun. So the project is coming along fast. This is a picture taken actually a couple of years ago when we were sort of in mid-construction on the telescope itself and the dome. Now everything is nearly finished. Here's an interesting picture. We were moving the mirror, the M1, M3 mirror, the big one, up from a storage shed up into the telescope. And, sort of from this standpoint, it almost looks like it's falling off the edge. But we made it up there, and I must say with some difficulty, because it was so heavy and it was sort of slippery. Travis, I think you may have been there for that.
Not for that one.
Not for that one. You were happily not there. Anyway, so the camera was built here at SLAC. And here's a bunch of folks, proud folks, displaying their camera here. It was boxed up and put on a 747 at an unannounced time in the middle of the night in May, mid-May, flown down. Here's the landing at Santiago. You were there, I think, and unloading, chartered flight. And so this experiment, we didn't want to wait for the main camera because there's a lot of worries that we wanted to be sure that the main camera was working really well. So we built something called the commissioning camera. It's basically a camera that is mounted at the same place in the telescope, but a single raft of a 3x3 array of CCDs that you can see here in this picture. And you can, I don't think this is going to work on this computer, but you can get hold of, this image is public. I could show you how to get to it, but you can zoom in, whoa. You can zoom in, maybe. See if I can do this. See how far this, you can zoom in all the way to very faint galaxies if you take a look at this image on the web. So that's available for fun. So we have, the commissioning camera has been on the telescope for a few months, and we have a lot of data which we're about to share with the world very soon, actually. So here's an origin of a problem with our charge coupled device. Astronomers are greedy, and one aspect to our greed is that we wanted to scan around the sky fast, and which meant that we would take basically short exposures at every point on the sky. If you're taking short exposures, you want to read out your camera fast compared to the exposure time. And so we very early on in the project set a limit at 2 seconds for readout. We have to read out everything. We read out 3,200 megapixels in 2 seconds. Well, it turns out you can't do that with charge coupled devices if you don't parcel the real estate on the chip differently. So we split up our chip into 16 sub-CCDs, each of which reads out through an output amplifier that's on chip. And all of them get read in parallel out simultaneously, so we get a factor of 16 speed up. So we're able to do this in 2 seconds. This gives us a problem, which I'm going to go into in a second. And that's it. That's the problem. That is a satellite trail that we have imaged in the lab. This is a lab image of a simulated satellite trail. We built a simulator that gives the identical same image, the same beam that the telescope gives to the CCD, but it's in the lab at UC Davis. And you can see a problem here, mainly that there's the satellite trail, but then there's also parallel ghost trails. That's because one output amplifier is affecting the voltage from the other output amplifier at the same instant that signal is going through both of them. And so this is called crosstalk. And it would be very simple if it was just capacitive coupling, because then it's easy to correct for. You just subtract it off. You just measure the coefficients and subtract them off. But it's nonlinear, and we don't fully understand all of the origin of the nonlinear nature of the chips. It's nonlinear, which makes it extremely hard, in fact impossible, to fully remove it in instrument signature removal in the data processing. So this is an issue with bright satellites. So crosstalk is one issue. This is just an artist drawing of the raft. all the electronics for the CCDs in a given raft are behind the raft. So a lot of us in the early days when we were building CCD cameras were spoiled by being able to put up all of our electronics outside of the camera, big racks of electronics. Can't do that here. You have to put it in the doer, otherwise you'd have too many wires coming through. And so optical fibers instead for us on this camera. It's nearly complete. We've spent nearly all of the construction funds now, and we're waiting for operations. That's an example of the telescope taken not long ago. It's nearly complete. Here's a view in the control room operating the telescope. Data is streaming off. Well, data from the commissioning camera is streaming off and being analyzed at the US data facility here at SLAC. So ship it up through optical fibers to SLAC and analyze data. So you ship your computer program, you ship your question of, if you want to ask a question of the universe, you ship your question to SLAC and do your analysis there rather than to put all of the data on your computer. So I mentioned earlier that it's important to be able to combine all of the data that we get with data from other facilities in order to get higher precision. And this is an example of other views of the universe, things that go off in the ultraviolet, the infrared, and the radio. And there are facilities that look at all of these things, and we're going to combine our data with the data from these facilities. And here's the names of them. And some of them are already built, some of them are about to be built, and some of them they're still searching for funding. But there's a very rich multi-messenger astronomy story going on now. So you might ask, so this is all data-driven science, right? There's so much data that you can, instead of posing your favorite theory, you actually let the data drive the model. So no longer limited by sample noise, which is a really good thing. And it allows you to discover new phenomena which you hadn't thought of. You haven't thought of a new, so you don't have a model, a personal model of what's going on. But then, do you trust the data at the level of precision that you probably will need? And do you trust the simulations that you have to, so you have to do a simulation of the data and compare it with a model, a simulation, and compare it with the data. This is a catch-22 issue. Ask me later. There are ways around this, but it's complicated. So here's the bad news. This is an amateur astronomer in Canada was following a comet. He had an f2.8 little telescope, 8-inch telescope, exposed for 25 minutes, and this is what he saw. This is recent. Not good. You can see all the stars moving a little bit because he was tracking the comet, and look at all those satellites. Here's a similar issue. This is the Hyper Supreme camera, the Japanese telescope on Mauna Kea. And this is a 50-second exposure, not all that different than what we're going to be doing. And there are 3 or 4 satellite tracks in this. And it's only a 1.5 degree field. We have a 3 degree field. And so this is the rest of the bad news. Not sure where to start with this. This is the total amount of traffic, launch traffic as a function of time. This is not a log plot, folks. So this is just a runaway. At the moment, over 8,000 SpaceX Starlink satellites have been launched up until last week. This is the number of filings with the International Telecommunications Commission Union. If you want to launch a satellite, you have to file with the ITU. There are over 1 million filings. You can see this going through the ceiling. And even worse is that there are all sorts of pieces of satellites that are up there. There's a lot of space junk up there. And so this is a total number of tracked objects as a function of year. And you can see debris. You can have, there was a Chinese weapons test that you probably heard about here. There was an unexpected collision here. Anyway, it's pretty hopeless. So the next decade is a new era in low Earth orbiting satellites and LSST, and we're not going to be able to avoid them. There's a lot of investor dollars pushing these guys to do bigger and better satellites, and so the conclusion of this talk is going to show you a little bit about what we've been trying to do to understand that and working with the satellite companies. So this is how it works. The sun, again, not to scale, the sunlight comes over here, reflects off of the nadir, the bottom surface of the satellite, and down onto your telescope. Part of the solar array, of course, can be seen at different times in different orientations. By the way, there's also something called earth shine, where the sunlight bounces off the Earth and up off of the satellite, and that actually creates an observable effect as well. And so satellites are getting bigger and better. It used to be that satellites were originally, and this is true of SpaceX even, the satellites were being built really just for communications, to take data and transmit it down to ground stations, and then put that data onto the fiber optics. That was the original business model. It's changed. Everybody has jumped on this big, important bandwagon of being able to communicate. If you're out hiking in the middle of nowhere, and there's no cell phone tower, just take your cell phone out, and you can communicate direct to the satellite. So that is about a 250 dB path loss. So you have to have much more intense beam from the satellite and much more power in order to do that. That's interfering with radio astronomy and also optical astronomy, because the intense beam is obtained only by having a very much larger phased array. It's simple diffraction, 60 lambda over d. So if you want a narrow beam, you have to have a very large array. So these arrays in satellites are huge. Here's a couple shown up here. This is one of the new generation Starlinks on the right, and this is a Kuiper prototype seen from space. And then if I can play this movie down here, take a look at what happens on the lower right. This is during sunrise. You will see Venus rising to the upper right. This lasts for 45 seconds, 4 a.m. Guess what? See those things in the middle? Those are flares of that's light reflecting off of pieces of the satellite that are basically flat mirrors, causing these flares. And we see quite a lot of those these days. You can go out in a nice dark place and see them every night now. You can see these flares. Either depends upon your personal clock, but in the morning or in the evening, you can see them both. So in the lab, we test these CCDs. As I mentioned earlier, we imitate the effect by illuminating. This is basically a huge double microscope. It has an input aperture about this big and an output aperture about the same. It's a one-to-one, the world's largest one-to-one microscope, and it creates a beam that looks just like LSST. So we do that, and so this is the ideal situation if we didn't have any crosstalk. Well, unfortunately we do. So this is what it looks like on an individual CCD. We have the main satellite trail and all these echoes. But then...
Is this looking near dawn and dusk, or this is looking at midnight when you still see?
No, this is in the lab. This is all lab-generated data. Okay, this is
corresponding to near dawn and dusk.
Yeah. Well, we're going to have one of these satellites in every image that we take, even pointing up in at the sky in the middle of the night. This has been seen.
You can still see.
Yeah, we just. So I had an undergraduate. He's the lead author on a paper that we're about to publish that tells us what we're going to see, and the news is not good. There are also very, very big satellites out there. A company decided not to worry about the light pollution problem for optical astronomy, and they have a giant, many sort of 10 by 10 meter surface of these Blue Walker satellites that are basically painted white, that reflect in all directions. And these Blue Walker satellites saturate, they go through about 12 CCDs on the average, they will, and they saturate the CCDs that you can see on the right. But most of the, so SpaceX has been very responsive to our measurements at the lab. They're interested in it. The industry best practice has reduced the tracked magnitude. That's to say the apparent magnitude if you were to track the satellite as it's moving. So just measure how bright it is in terms of apparent magnitudes, to about 6.5 or 7 magnitudes. Your eye can see about 7, especially if you're young. So those of you that are young here, if you let your eyes dark adapt for 15 minutes and you're in a really dark place, you can see 7th magnitude. I'm an exception. So that's the good news. But the bad news is that we're supposed to go to 24th magnitude in an individual exposure, and to 27th magnitude in combining the exposures to do all of the fixed astronomy, like cosmology and galaxy evolution. So this is 500 million times brighter in the optical than we can suffer. So it's like you're driving down the road and you have somebody with their brights on and you can't see the kid walking across the road, right? It's 500 million. It's a big number. Radio is even worse. They're over 1 billion times brighter in the radio, simply because they're broadcasting so much power, 50 kilowatts. So there's a problem. The other issue is that even if you tried to correct for this, you end up with problems because in doing sensitive experiments in physics, there's always a trade-off between accuracy and completeness. You're somewhere on this curve. You can have a complete survey with very poor accuracy, or you can have an accurate survey with very poor completeness. And this is, engineers call this the receiver curve. That's because it's true in all branches of science. And so the issue is that we can find, occasionally we can find most of the satellite trails, but sometimes we miss them because satellites change their brightness as they're moving across the focal plane because the angles are changing. And you can remove them occasionally from images, but this is really hard to do in all cases. It's been such a hard problem that we've decided just simply not to fix it and let the astronomy community try to deal with this in their own data reduction. And then, of course, on top of all of that, we have the concerns that I showed you before of glints and flares, which interfere with the time domain announcements. Yeah. So we have to be careful not to alert on assets that we know our government knows about in the sky, and so we have agreed not to do that. They are supplying us with a list, and so we don't do that. But then the data is available a number of hours later, so we can release it later. So there are a number of challenges that I list here. The streak signatures and survive even if you try to combine images with some of them with satellite tracks are removed. They exist in the variance plane because there's one image where you've removed the satellite track and the noise is weird. It's correlated noise. And that feeds through the variance plane. So when you finally get all of these co-added images from which, after 10 years, we're going to be doing all of our deep cosmic shear analysis and galaxy analysis, there'll be a signature there that bleeds through. Moreover, I mentioned that there are these debris out there. There's over 40,000 tumbling debris that are the size of your cell phone, which gives us a fairly big signal when that flat mirror reflects the sun into your telescope. And they're tumbling, and so you have these little beads, dots across the focal plane. This is from the Zwicky transient facility. Has a small focal plane compared to ours, but you can see some examples of these here. So it's a big challenge, all sorts of stuff out there. But here's some good news. So most of the low Earth orbiting satellites are close compared to the distant universe that we're focused on. So we have a very big mirror focused at infinity, right? And so the stars are in focus. So look at the bottom panel here. So here's a star in focus. This is a simulation of LSST. But if you have a satellite at low Earth orbit, this particular one we simulated was a 500-kilometer orbit. It looks like the thing on the left because it's out of focus. And moreover, it's moving. And so it's moving this out of focus blob across the focal plane, which creates even fewer electrons per pixel in the camera. And so these two things combined give us a partial way out of this, but not complete. But there's something interesting, which I'm going to close with this slide. So we did a simulation of just the first few hours of observing in the evening under two circumstances. One, putting all of these all the SpaceX satellites at 550 kilometers, where they primarily are at the moment, and the other, moving them down to 350 kilometers. And you would think by 1 over r squared that they would be a whole lot brighter. The sun doesn't change. They are brighter, but they're more out of focus. And the two things together cancel. On the right is if you move them down, and so these you have to add everything. You have to add all of these histogram bars together. This is the number of LEOsats per hour in the focal plane, and on the left is at 550 kilometers, and you can see you have quite a few more. But this is just based on the LSST observing schedule and sort of a space-time ephemeride issue with regard to knowing where the satellites are. If you then add the effects of the out of focus, the conclusion is that the surface brightness is nearly the same as at 550, which is really good news. There's no reason why they shouldn't do this. And so our advice to them is to move them down. It's also a good idea because then if something goes wrong, it'll burn up in the atmosphere. And this is the undergraduate Fan Kandula who leads this paper. He's now off to graduate school at UMass. So that's the end of my talk. Open for questions. Thank you. Yeah.
Thank you, Dr. Tyson. Is there any interest from the satellite vendors in producing less reflective surfaces?
Yeah, and so everybody's trying. What SpaceX has done, counterintuitively, they started with painting it black. That didn't, well, it made it dimmer, but their output amplifiers on the transmitters burned up because it's hot. The sun hits something black and it heats up. So that didn't work. Then they tried basically solar shields, little plastic shields that like a tent at the beach. That worked until they decided that they wanted to use lasers to communicate to other Starlinks at different orbits, and so it got in the way. So they had to give up on that. And the way they designed it, they put it together by just going to the local Ace Hardware and buying some stuff and launching it. That's the way they do things. And so then they tried something counterintuitive. They tried to make the bottom surface of the satellite a mirror, a really excellent mirror. And if that's really good, the sunlight will reflect off of the mirror and off into space, not down into your observatory. The initial attempts at this weren't perfect. It had a little, so they roll this stuff on. They call them stickies because they roll it on and it sticks to the aluminum. But they've gotten really good at this. And the modern, the so-called V2, Gen 2 satellites that they have really, really good mirror surfaces. And most of the reflections of light are not off of the bus of the satellite, but they're off of pieces of the pieces of the rest of the satellite are out there. These solar panels and the edges of the solar panels and the cantilevers that hold it. But they're trying hard, but it's still too bright for us by many magnitudes. Dan?
At midnight, how bad is it? Or is
It's
by light off the moon or?
No, no. So we don't fully understand. So we predicted this in this paper, and sure enough, people are seeing these Starlinks now at midnight. They're at 5:50 at the moment, but we see them at midnight, and we don't quite understand why. To tell you the truth, the engineers there are pretty free to play around. That's the way they operate. And so just before launch, they go in and they, well, I want to put my little thing here. They put something on, and it's not painted black, and it's a mirror surface, and stuff like that happens a lot. But no, I think it has something to do with the solar panels. They're up there, and they're up high enough that they're getting some sunlight on them. They're sort of in the shadow, but partially out of the shadow. So if you're down low enough, you're completely shadowed by the Earth. But if you get up at this altitude, and anything higher than 600 is really dangerous. And our committee, we had a committee already about 5 years ago that required that the FCC we suggested that the FCC require that satellite builders and operators operate below 600 kilometers for this reason. Because if you go above 600, and there are many communication satellites that are at 1,200 right now, including Blue Walker, they are reflecting sunlight, bare sunlight, right down on the ground in the middle of the night. No, we don't fully understand. Roger, you have a question?
On the same theme, as you have more satellites and more debris in space in the future,
Yeah, that goes hand in hand.
How concerned are you about the probability of collisions?
Yes, yes,
I mean, do they have avoidance protocols in these satellites, like
yes.
the satellites we know and love have?
So there was a study done by an outfit called Jason. Some of you have heard of Jason. It's a group of physicists that get together to advise the government. And they concluded that as soon as you get more than 40,000 satellites in low Earth orbit, you will have this is called the Kessler syndrome, where you have so many satellites that the probability of collision rises quite a lot. Even today, and this is public, I'm pretty sure, even today, SpaceX has to avoid something 200 times a day. They're making orbit moves of their satellites 200 times a day. And this is with only 8,000 satellites.
The cowboy satellites have avoidance.
Yeah. Yeah. Anyway. Yeah, so it's going to be exciting looking through this foreground at the distant universe. Yeah.
Apropos of that, you show this huge growth that's just going nuts.
Yeah.
When is your estimate when that will prevent you from doing the experiment?
Good question. Personally, I think we've done this analysis actually. It's not public, but it's not going to last that long. Maybe we can continue. So this is going to come to a peak, it turns out, around 2035, because more and more satellites are being launched, and so if you're going to have a problem, it's going to really peak around 2035, which is sort of in the middle of our survey. Okay.
Why will it go down?
Well,
after 2035?
Because more and more satellites are going to be launched, so we're going to have at least 100,000 of these satellites, more like 1 million. The number that's up there is rising.
Won't it just continue to get worse and worse and worse forever?
Yes, but then our survey ends at some point. And so
that's the answer. It's maybe 50 years.
Yeah, that's the answer. Okay, thank you.
Sure. What are your limits? Why don't you pursue satellite-based?
That's an excellent question. I get asked that quite a lot by reporters, and the answer is that
What other option do you eventually enter?
there is no option. The answer is interesting, and that is, they ask me, everybody's building these giant space telescopes. Why don't you also put all of this in space? And so, remember, we have to.
I'm not encouraging. I'm asking.
Yeah. So to answer your question, we have to point in different directions every 30 seconds, or even less, moving around the sky. And how do we do this? If I'm trying to move. So if you're trying to move LSST, you know how heavy it is, and it's pushing against the ground to do that. It's a lot of force. And you have, I think, personally done that yourself, pushing on it. And you pushed against the concrete to do that. Well, there's no concrete in space. So there's nothing to push against. So you can't do it. That's the answer.
Well, what is the ultimate? Are they going to stop launching satellites? But it doesn't sound like they're going to do. But after 50 years, are you just going to give up the ghost? I mean, there's got to be some.
Well, this particular wide field, very rapid, wide, fast, deep survey is impossible to do from space for a couple of reasons. I just gave you one. There'll be other experiments that people do, but they won't. No one else is doing this kind of experiment because it's huge. It's pushing technology quite far. And my own view is that it's two examples of beautiful technology. To be able to talk to your cell phone directly from space and to be able to do this experiment. They're just on a collision course.
it's getting late, so let's thank you.
Yeah, thank you.
Hopefully be a few minutes if you have more questions.
I didn't realize that.
Donations?
Yeah, no, I was thinking, I learned about this U.S. security.
Oh, yes, yeah.
So it sounds like that's actually solved now?
Yeah, yeah.
So you're not going to try to.
There's a reason, and that is